So just to kind of start our conversation, maybe what prompted the development of the company's new KVA 38 electric valve actuator? Was there a kind of a need in the industry or some sort of other industry driver? Or
Yeah, so the KVA 38 development started back in 2019. Back then, Kinetics Automation was involved in a variety of motion control technologies, including linear actuators and hydraulic piston pump actuators. And we were approached by the Natural Gas Innovation Fund, which is a clean technology arm of the Canadian Gas Association. And they brought a problem to our attention, and that problem was methane venting pneumatics. Back then, I was aware that the natural gas industry, was in the news for methane release, and I was under the impression that it was all, let's say, accidental release. There's a leaking valve, a leaking pipe, leaking equipment, methane's going into the air. Obviously not a good thing, but repairable. But once we dug into the problem of methane venting, we came to appreciate that there's equipment, pneumatic actuators, valve actuators in particular, that are designed in a way where they're using the gas from the pipe, essentially from the ground, as a source of compressed gas. Or, we would think of it maybe in a traditional manufacturing facility like compressed air. But no, it is gas, methane gas. And the way that they're using it is to consume or use the pressure for useful work. But they don't combust the gas. So after the valve actuator does its job, it's releasing, sometimes in puffs or sometimes in a continuous way, methane into the atmosphere. And this kind of practice is now starting to get phased out for a variety of reasons. And they were interested in trying to develop solutions that could go in and replace the polluting technology with basically a better alternative. And this is where we sharpened our pencils, really attacked the problem with support of industry, and came back with a general purpose glow valve actuator to address a good portion of the equipment that's currently running out in the field that's operating on this methane venting strategy currently.
Mhm. Okay. And so could you maybe then provide a bit of an overview of the technology itself and its design? And I know it's told it, uses a shape memory alloy technology. Could you go into that as well?
Yeah, definitely. I've got a full-scale sample of our product just here to my left. So I'll start from bottom to top. Because we're using a different drive technology inside, it probably looks different than other valve actuators on the market. But at the base, we would have a stem, which is the moving end. And this is what couples to a globe valve. So a globe valve would typically be it does look like a globe, but in fact, inside they have a moving stem, which is an up and down motion with something called a plug. You could consider it like a cork, and it fits inside of a hole, otherwise known as a valve seat. So we're able to connect to that valve stem and control the position of the valve. There's mounting hardware that would also mount onto the valve body itself, so you have a nice solid connection. And then up from there, we would have a control panel. So you would access that for one-time hookup of the electronics by taking the panel off. Wiring comes through on two ports. One would be for power, take 24 volts DC or 120 volts AC, depending on the SKU. We would also take in a signal, and that can be a variety of different industry standard signals, like as simple as open close commands, or we can take an analog 4 to 20 milliamp signal. We even have a Modbus port for customers that want to get a little bit more out of their actuator. So from there, we take the power and the control signal, and then this device will energize a shape memory alloy actuator inside this main tube section. So a shape memory alloy is a special kind of material that is able to change its shape. So we're talking about a metal where we can control the length of it by exciting it with the electricity that's supplied from the site. Opposing the shape memory alloy, which is something that basically extends and contracts, opposing it is a very traditional valve spring, which I've got a sample of here. So this would live inside of the housing. And basically this is the spring, albeit in a compressed form. It puts out for the KVA 38 about 900 pounds of force, otherwise known as thrust. And when the device is idle, it's the spring that's pushing down and holding the pressure in the valve in a closed position. When we want to open the valve, this is when we flow electricity through the SMA material. It compresses the spring even further, lifting the valve plug off the seat, allowing those gases to flow. And it's a very, how do I say this, controllable technology. So we can set the position extremely fine, so 50 microns or 2/1000ths of an inch. And this allows for modulation or throttling of the gases or fluids through the valve. Maybe just to finish off on the mechanical side, we include a drip cap on the top because it's good for indoor or outdoor location. And we also include a little eyelet at the top for easy rigging for first time installation, or if you need to lift the actuator off the product, off the valve to do routine maintenance on the valve.
What makes this technology different or unique, or are there other I don't know, similar or other types of electric valve actuators like this in the market that are attempting to replace pneumatic options? And what sets your technology apart, I guess?
Thanks for the question. So the shape memory alloy technology is very different than pneumatic actuators or motorized actuators that are currently on the market. I think one of the main reasons we were approached initially was because the industry has become quite accustomed to and reliant on spring-loaded valve actuators. The reason for that is you might hear terms like fail closed in reference to a particular valve setup. And the reason for that is due to any kind of an interruption on site, be it loss of power, loss of the control system, or sometimes even just failure of the actuator itself in some way. The spring inside biases the valve to a known position, and then the designer of the system can have some peace of mind that, okay, even when things go sideways, at least I know that the system biases itself to a safe state. So for those pneumatics to work, they flow the gas in to compress the valve spring and to lift the valve, and then again in a interruption event or sometimes by design, to lower it, the gas is released and the spring takes over. But there's really no analogy to that for electric motorized valve actuators. So these are the other types of actuators out there where you would use a rotary motor, brushless DC as an example, sometimes even AC motors on those larger actuators. I think a few of your readers would recognize these as those ball screw actuators that are used for a variety of different things. You can think of that vertically mounted on a valve, that kind of arrangement, where they have to take the rotary motion of the motor and somehow translate it to linear, which is sometimes a challenging prospect when we're talking about hundreds, thousands of pounds of force, or kilonewtons of force that need to be applied on the valve. So that mechanism tends to add a lot of cost, complexity, and maintenance parts. And depending on the design, when there's a failure, there's no spring inside these motorized valve actuators, so they tend to fail in the last position. And it doesn't necessarily mean a failure of the device itself. Sometimes the power, which we tend to work at remote sites for a lot of the natural gas customers we're serving, you now have a situation where it's spotty power at best. The device fails in an open or partially open position, and now you have a situation where the system is not biased in a safe way, and you have uncontrolled flow of explosive gases and liquids. Obviously bad. So let's say look at our technology. We are able to kind of maintain or retain that traditional pneumatic actuator spring, so we can bias the device to a known position. But our shape memory alloy actuator develops its force in a very linear fashion, which is completely in line with the valve stem. So what that means is we have no need to do any kind of fancy mechanical leverage or conversion. It's a very simplified architecture, which allows us to kind of work in a way where we're not on metal at any point. In fact, it's basically a floating design with one moving part. Really, the only thing that's touching the valve stem on our end is just a wiper seal to keep out dust, debris, etc. But it's otherwise floating, so the kind of typical failure or maintenance points you might see on other actuators is completely eliminated. And we're able to kind of provide that very smooth motion because we're not kind of grinding gears, etc. So the kind of response you can expect with this motorless drive technology is, for one, it's 100% duty cycle. That means we can go constantly in motion. For us, there's no wear and tear cost to changing direction. And as a result of that, we can completely eliminate deadband. Whereas motorized operated valves or sometimes pneumatic valves need to pause between changing directions. For us, it's just as fluid as my hand is moving. It's a very natural thing for the product just to follow the command and provide that fluid motion. And part and parcel with that we kind of eliminate any kind of typical backlash you might see, which ultimately degrades process control solutions where, inserting this backlash or these deadbands ultimately start to stack up and you get a better, not as effective control, I'd say, on the site. So, I know I've said a lot, but combining kind of a linear drive technology with spring failure and low maintenance, we believe we've got a very, suitable product for our customers.